So we assume that we have our what we call short exact sequence of chain complexes. So there are triple chain complexes A, B, and C. So we all know the sequences the composition of D of two consecutive Ds is trivial. And also we have in this diagram each column is short exact sequence, which means that each I here is injective, each J is surjective, and the image of I is the same as kernel of J, and everything is commutative, which in particular every square is commutative. Okay, so and we showed, so last time we showed that we could define this map from H and C to H minus 1. Okay, and essentially it was taking some element here, which represents a class in nth homology of C, and going like this in the diagram to get an element here, which represents a class in this homology. Okay. Okay, so once we have this map, we can show the following theorem. The sequence so we already wrote this sequence last time between homologies. So we start with a long sequence. So suppose at some point we have homology of A, then we connect by the induced map I star to a chain of B, and the induced map of J star takes us to a chain of C, and then we use the delta map to get to jump with one index to n-1 A, and then we repeat this. And so now everything here is defined, and to remind you, the I star and J star are defined just because of the I commutes with D. Right? So it's a chain. So the statement is shown before, this sequence is long exact. In particular, this will so we know if you, for example, you saw that if you have a if you have, for example, short exact sequence, you know some part of the short exact sequence. This gives us a lot of information about other groups which enter in short exact sequence. So in particular, we know some of these groups, and we know that this is a long exact sequence. This can allow us to calculate in certain cases some missing groups. It's a very useful tool in general. Well, this is so far we're working with abstract complexes A, B, C, but then we can apply it to our story of singular homology. Okay, so how do we prove it? So we will need to prove exactness at each point, at each group. At each place here, we need to show that the kernel of this map is the same as image of this. So let's start at, so the easiest place is actually here. So we want to show that the, we want to show that the kernel of J star is the same as image I star. So let us show it in two steps. So we can show the kernel of J. First, let us show the kernel of J star contains image I star. So this is pretty easy. Let's see. So we have we already know that for the maps I and J themselves, we have this condition because this is a short each of the columns is a short exact sequence, in particular the kernel of this map is image of this map. And then if you calculate the induced map for both sides, you have that the composition of the induced maps is also trivial, and this essentially applies this property. So this was easy, but the other parts will be more difficult. So now we also want to show inclusion in the other direction. The kernel of J star is included. This is a short. Included in the image of R star. Okay, so let us take some element here, beta. The class of beta. So beta. So this is a kernel of J star. So you take some element in cohomology H and B. So it's represented by some cycle beta. So the d of beta is 0, since this represents a class in homology, and beta belongs to Bn, right? So this defines me a class. Particularly this guy sits somewhere here. Okay, and we know that so it's more weights in the kernel of J star, so we know that J star is 0, and but by definition of the induced map, this is the same as a class of J of beta 0, and which means that so this is the classes in homology is 0. This means that so we have somewhere J of beta here. This means that J beta should be equal to a boundary of some gamma, which is here. Okay, and so we know that J is surjective. This means that there so for any gamma, there exists a mu such that gamma is J of mu. So mu, so J is surjective, which means we can always find the image, some image mu of gamma. And so then we calculate. But then we can send this mu by acting by d somewhere here, d mu. And so if we do it like this, we want to compare now with this beta d mu. So let us consider the difference. Consider the difference, and what happens if we consider this difference and take it downstairs by j. So this will give us, so j of beta is d gamma, and so j commutes with d, so this is the same as d of j of mu, which is also 0 gamma, and this is 0. Okay, so this means in particular that beta minus d mu is inside the kernel of J, so the difference is set to 0 here. And but you know that the kernel, so this is a short exact sequence, so the kernel of J is image of I, and this is, so So this means that this difference, so this is an kernel of J, so this means that this difference can be, so since I is injective, well, let me, sorry, before using the I injective, so we just say that since this is an image of I, there exists alpha, so there exists alpha here, since it's an image such that I of alpha is equal to beta minus d mu. Okay. And okay, so we know that let's see. Okay, so what happens if you calculate d of I d alpha? So we d alpha is down here. What happens with R d alpha? So this is so this is the same. So I can commute d and I here. So d I of alpha, and then this is d of beta minus d mu, which is the same as d beta, because d squared is 0, and this you know is actually 0 because beta was a present element in homology. So this is 0, and so we know that this happens to be 0, and since I is injective, this implies that this d alpha is also 0. Okay, so this means that in particular alpha, the class of alpha, I can consider the class of alpha in homology of A, and then I can calculate I star of alpha, which is by definition the class of I alpha, which is the same as, well, we know it is I of alpha, so it's the class of beta minus d mu. And since d mu I can omit in my class, this is the same as class of beta. Okay, so now we arrived at the fact by doing, so what we did here is some sort of diagram chasing. So we found alpha such that beta is I star with alpha. So we started with any beta which represents a class in the kernel. This means that beta is in the image I star. So this is what we wanted to show. So this element here also sits here. Okay, so then we show that the kernel of G star is equal to image. So we checked exactness at this point. Any questions? Okay, so now we want to check the exactness in another place. So we want to check that the kernel of delta is the same as image of G star. Again, let us split it into two parts. So first, let us check that the kernel of delta contains image of G star. Okay, so let us take some element here, it's represented by class of gamma. Should erase. Class of gamma, and each plus 1c, let's say. And so necessarily gamma should be 0, and there exists so let me actually take gamma. Doesn't. This is what it is. So this means that so it's in the image of J star. This means there exists some alpha in this image of J star. So there exists some alpha here. Sorry, not alpha was this mu such that well, it should represent the class in homology, so d mu should be 0, and J star of mu should be equal to gamma. Okay, good. And of course, this is the same as class of J of mu. Okay, so now we want. So let us consider. So we want to check this is in the kernel of delta. So we want to act by delta on this and check that this is 0. So let's do this. Okay, so delta of gamma is equal to class of alpha by construction. So by construction, if you remember how we construct the delta, we need to go like this. So here we have our alpha, and somewhere in between we will need to choose beta, and beta here. And in the intermediate step, we need to go like this. So we need to choose beta such that gamma is equal to G of beta, and D of beta equals alpha. Okay. And we see that we can solve this equation by taking actually beta to be mu. So let's take beta to be mu. So because this, we can solve this by taking beta to be mu, and so let us. So this thing then should be equal to d mu, right? And since we know that so we know that d mu is actually 0. And well, we also know that I is injective. Then this implies that alpha itself is 0. And well, this in turn implies that delta of gamma is a class of 0. So we checked this conclusion. Now I want to check the other way around. The kernel of delta is inside much star. So let's take some class of gamma here. So gamma is being sits, but it's still here. And so of course represent an element in homology, so it's d of which should be 0. And more it's in the kernel of delta, which means that delta gamma is 0. This means that by definition this is a class of alpha, which is related by going like this. Namely by solving the following system of equations. And so this is 0. The class of alpha should be 0. So this means that alpha is equal to d of something, so mu. So this mu is a preimage of alpha under this arrow. And so then if we, so what about beta here? So beta, from this we learn that the d of beta equals to I of d mu, is the same as d of I of mu. And so in particular, this means that d of beta minus I of mu is 0. So I of mu. Take mu this way, the difference between I of mu and beta is sent to 0 under this arrow. And so let's see. So if you take in particular, this defines me some class in homology. And so if I take j of this difference, this is the same as j of beta, because the composition of j is I is trivial because of short exactness. And and this we know, the right hand side we know that this is gamma. Because of this. So since this defines me some element So, but this defines me some element in homology. So I get equation that so that the class of this is the same as J star of a class of this. And the class of the right hand side is the class of gamma. Okay, so yeah, we found some element beta minus I nu is so we showed that this difference of those two guys and J is sent to gamma, well, up to total up to d of something. Well, actually, yeah, no, this is even true without. So we check this inclusion. Well, so we check the kernel. So we check this. Questions? Now the third part we want to check is the kernel I star is the same as image of delta. It's exactly the third place. So again, let's check if the kernel, so the image of delta is inside the kernel star. So this is so the element of the image of delta is of the form delta of something, and so where this something is a class of gamma, then gamma must be such that d of gamma is 0, and okay, so I need to check that this is this element of this form is inside the kernel of I star. Okay, so let's just act by I star on this guy. So again, we remember how we, so the action of delta is again constructed. I go like this, solve this system of equation. Alpha, so this will be I star of alpha. And more specifically, so gamma is repeating this gamma and J beta and D beta is alpha determined by this system. And well, since so I star of alpha is the same of class of alpha is the same as I of class of I of alpha, the same as class of D of B. Okay, and finally, we need to show the other way around. Okay, so so we take some element here, say class of alpha. Take some element here, it's a class of alpha, and so we just cube into small this I. So again, I need to should be representative of homology, so d of alpha is 0, and moreover I star of alpha, which is the same as class of I of alpha, is 0. This is the kernel. Okay, so this means that there exists, or the class of this guy is 0. This means there exists beta. So let's see, the I of alpha is here. And this has a trivial, this is trivial in homology. This means that it's equals to, so there's some eta here. And so this is d. It's in an image with this demo. So there exists eta. Eta such that I of alpha is d eta. Okay, so now, so what happens if you calculate delta? So we take now we take j. So we want to, also our goal is to show that this is in the image of delta. So there is something which sits here. So if we apply our procedure, we get alpha, we get class of alpha. So but let's so we found some eta like this, and let's send eta here. So it will be j of eta sitting here, and let's check that this is actually will be. If I add it by delta analysis, I go there, I go back, I do recover my alpha. Okay, so, well, actually, first we need to check that this is define some element in homology. So we need to check that this is 0. Otherwise, this statement wouldn't make sense. But this is of course true because this is d. I can commute as usual these guys, and this is 0 because. Sorry, wait a minute. Sorry, too fast. This is j, so d eta was such that it satisfies this property. So this is j of I of alpha. Sorry, what's going on? Yeah. Okay. Yeah. This is this follows from the fact that this is short exact. Position of I and j is 0. This is 0. Good. So this is indeed defines an element in homology, and moreover, indeed, delta of j of eta is equal to class of alpha. So this is because this is because it solves this system. I mean, I can imagine that this is as before. I mean, to find alpha by a given element here, we need to find some beta which solves this system. So eta would be our beta as before. And this would be our gamma. So indeed, eta. So this is so we checked that this guy is in the image of delta. Check this, and therefore we check this. Combine the guys, we do. So we show that the long sequence is exact at all places. At all places, the kernel of the map is the same as the image of the preceding so now we'll come back to the topology. So there is some abstract homological algebra. And now let's come back to topology. So in particular, make the following corollary of this theorem is that, well, let's take a particular example of this short exact sequence of chain complexes. So we take chain complex AN to be complex of singular chains in A, where A is some subspace in X, and Bn chains in X, and Cn will be our relative chains, which are reminded by definition just quotient of these given groups. So we have this is so this sequence. So it kind of has the following short exact sequence of chain complexes. So this map is inclusion. And we go to Cn(x). So we show that these chains are naturally included in those chains. And then I take J, just a quotient of this quotient. This is short exact. And so we argue that these are indeed I and J are chain maps. So they come, namely the commute is D. So we are in a situation of the theorem we just proved. So therefore we learn the following statement that there will be the following long exact sequence of the corresponding homologies, which we defined. So this is to have the following form. Or just continue the second line. So let's consider the example of using this, of how I can use this statement to calculate some homology groups. So let us consider some rather generic situation where, let me take some point in the topological space X, and so A will be just a set consisting of this single point. Okay, so first let's see what happens, how this long exact sequence looks when n is greater than 1. This looks like this. So let me just write explicitly. So this is the Hn of my point, right? Then Hn of x. And it will be its relative Hn, it's relative to the point. And then we go like this. So we know the homology of a point. So we know that for n equals, if n is greater than 1, strictly greater than 1, this is trivial, and this is also trivial, right? So this map is necessarily trivial, and this map is necessarily trivial. Not 0. But then, well, it follows that this is isomorphism, right? Because we know that the image, let's see, so this the kernel of this map should be the same as the image of this map. So the kernel is the whole space, so this means this map is surjective. Similarly, the kernel of this map here should be the image of this map, which is trivial. This means the kernel of this map is also trivial. The kernel of this map is trivial, and this means that this is injective. So both surjective and injective, this means that this is isomorphism. Okay, so we learn in particular these two groups might be isomorphic. So you see, without actually doing any kind of topology, we were able, but using this theorem, well, of course, in order to arrive at this, we use some properties. We were able to find equality, to find these two groups are the same. So if you know this, we also know this. Okay, so what happens when n equals 0? So the end, how does the end of this sequence looks like? So this will be something like h1 of x0, h1 of x, h1 of x, h0, go down, h0, 0, h0 x, and 0 x relative to 0, and then it should be 0. So what do we already know? So we know homology of a point. So we know this is still 0 h1, but this is, we know that this is z. 0 homology of a point is z. And we also know what is h0 of x for general x. So we know this is a direct sum of copies of free abelian group for each connected component. The sum of connected components, past connected components of x. And okay, so moreover, we can argue that this map is injective. So why is that? From separating. So what is this map? This is so the map induced by inclusion from point to x. So we know that the what is the zero homology of a point? It's just generated. So this is z. It's those can be understood as a abelian group which is generated by sigma, which is a map from zeros simplex to this point. So, and there is a unique. So this is the delta 0 itself is just a point. So it's a map from a point to a point because there is a unique map. So there is a single generator z. This is what we already had this understanding. And what about h0 of x? So x, remind me, so that has this proposition. So x splits into past connected components like this. Then So this is a direct sum of copies of Z, where each Z can be understood as generated by some map from a delta 0. So it's a class of a map from delta 0, which is a point again to X of. And of course, so if you have some inclusion, so this is this map becomes one of this map depending. So if X0 sits in particular X alpha, then this generator of this guy maps to this generator, right? So this means that this is injective. This is injective. This means that the kernel is trivial. And we know the kernel should be the same as image of this map. So this map should be 0, should be trivial map. And so this is a trivial group, so this map should be also trivial. So again, if an exact sequence something is between, there are two guys sandwiched between trivial maps, so this is necessarily isomorphism, as we argued before, just here. And okay, and this is so since this is a trivial map, and that this should be, and this is also trivial map, this must be so this is this map is surjective. So this is the image. This thing is the image of the same guy, but the image we know, the image is isomorphic to the quotient of this group over the kernel. So this is isomorphic to this quotient. So essentially,
the injectivity is not simply because there is arbitrage from X to the bottom. The injectivity is not simply because there is arbitrage from X to a point.
Yeah. Well, this is what's that? No. So what do you mean? I mean, the injectivity follows from the non-trivial generator here and maps to non-trivial generator here. What do you want?
No, because I remember that in the homework we proved that if there is arbitrage, the inclusion is.
Oh, yes. Well, yes. If you, I mean, you can consider the retractor point. Yes. Yeah. You can use the factor. Yeah, you can use the fact that there is, I mean, you can always consider a retractor point, which means that this is injective. So this essentially means that this group is again Freiberg group, almost the same like this, but you just remove one of the generators, which corresponds to a connected component where this point sits. Okay, so by combining these results, we learned that the Hn of these related homology groups, so they're the same as homology of X itself when n is greater than 0 and H0 of X divided by Z when n is questions. So we define the homology of, so the relative homology is the homology of a pair. So the input data, the output is some abelian group, and the input is a pair of topological space. Topological space and a subspace inside it. So as for the usual homology, we want to consider some properties, how these groups transform if you consider some maps between. So the usual homology, we show the properties of how the homology transforms under some maps between spaces. So now we want to consider a similar thing for maps between pairs. So let us define what this means. So let A will be subspace in X, and B will be subspace in Y. And then we will use the following notation to denote F to be a map of pair XA to pair YB. If we have F is a continuous map from X to Y, such that if we restrict F on A, it will be mapped inside B. And so such map, which satisfies this condition, induces sharp, a map between so just on the level, just because it's a map from X to Y, so we know that this induces a map from Cn of X to Cn of Y, and we know there we have subgroups here Cn of A and subgroup here Cn of B, and because of this property, we know that F sharp of Cn of A will be inside, will be a subgroup inside the F sharp, so inside the Cn of B. Right? Because this is a chains, these guys are generated by singular simplices. So this guy is generated by simplices with images inside A, inside B. So if you have a singular simplex with image inside A, if you compose it with F, its image will be inside B. So it will be regular generated here. Okay, and because of this, it induces a map on the quotients. So you can see that there's a well-defined map on the quotients. Again, the elements here are represented by elements Cn of X, moduli elements here. But because of this condition, if we just take this representative and apply F sharp to it, we get a well-defined element here. Okay. So, and also because we had this property with the original map of sharp, it will since D, so we define D on these groups by just restricting D acting here, so this will still hold. And therefore, so whenever we have a map between two chain complexes which satisfies this property, it defines it defines the corresponding maps on the same formula. Take some class here, not F sharp. Close F sharp. So this induced map, the push forward on the other homology will satisfy similar properties to the push forward on the ordinary homology. So particularly if you have a so let us first define the notion of homotopy maps between pairs. So we say that F and G are homotopic as maps between pairs. By definition, this means there exists F like this, so this is like in the usual homotopy. So F restricted on 0 equals to F, and F restricted to 1 is equal to G, but moreover, we want to require that for any T in the interval, we restrict F at some point here, and take its image of A, it will be inside B. So we already know that this is a property is true by definition at 0 and 1, but we want to require this holds everywhere. Okay, and okay, so it's the definition of topic homotopy of maps between pairs. The pair is a topological space in a subspace. And again, we want to show this proposition, similar proposition. If F is homotopic to J as maps between pairs, it follows that their induced maps are the same. The induced maps from HN So what is the proof of this? So we already had this proof of this statement when there was no A and no B, just for the usual homology, and there we defined a so-called prism operator. So consider the prism operator. So we define the prism operator in from Cn of x to Cn plus y. So it defined using this homotopy, which we have. And so we know that because of this property, we know that P I consider P of the elements in the subgroup here, Cn of A, this will be inside C n plus 1 B, the subgroup. Okay, essentially P was constructed by kind of restrictions some restrictions on the subsimplices and compositions with F. But since the composition within F itself satisfies this property, so whenever you have this generator here, this image inside A will be marked inside this subgroup. Okay? And this means that again it induces well-defined map on the corresponding quotients, which I denote by the same letter. And also, which just use this. I use this well-defined map. This relation which you had before. So now this is considered as a relation between maps from Cn of Cn x comma A, which is this portion, to Cn y b. So the statement that this is 0 it still holds. Because all this map is just the same as the map before, just induced on the portions. And well, we know with general remarks that whenever we have this the relation like this between two or exists a P some homomorphism P like this, so the difference between two chain maps is of this form. We know this immediately implies that the induced maps on homologies, they'll be just the same. I'll show this. Where's the chain rule? So we call such maps chain topic. Questions?
This trace operator didn't decrease the.
No, it was increasing, exactly because you consider its composition with D, which decreases. It was increasing because on the prism, it was a prism because it's so we started with some n simplex, and then you extended it to the prism, which was then split into n plus 1 simplices. So it increases the n. Questions? Okay. Well, now is quite an important theorem. This actually will allow to, basically will allow to calculate, relative, some other relation between relative homologies and non-relative homology, and will allow to calculate homology groups in various situations. So there are two versions, which are current versions. Okay, so version 1 is the following. So let Z inside A, which is inside X, such that the closure of Z is inside interior A. And so the closure is Z itself, including all bound points. Okay, and then inclusion map is a map, consider as a map between pairs. This is complement. This is what is X. So this is indeed about defined map between pairs. So if I consider, well, this, of course, X minus Z is included in X, and if I restrict it to to this subspace, this will sorry, what? Yeah, this will this will map inside A, because this is inside by definition. So this inclusion induces isomorphism. Between the corresponding homology groups. So this is version 1. And what about version 2? So version 2, we have a following A. We have a pair of subspaces in X, and it requires that their union of their intersections covers the whole space X. And then, so if we consider the, now I want to consider the following map between pairs, so inclusion into, well, B is included in X, and this intersection is included in A. Just inclusion map induces again induces isomorphism. So why is it equivalent? So first of all, the proof will be later. A little bit later, and but why are they equivalent? It's actually easy to see that they're equivalent. Corrections. So they're equivalent just by redefining what is this A and Z are. And the relation is like this. So the B is X minus Z. The B here, so the A here is the same. I take A here is the same as A here, but B and Z related like this. So B is a complement of Z in X. And so in particular, this it follows. So if I take intersection, so this X minus Z indeed gives me B, and if I take the intersection of A and B, this is the same as indeed A minus Z. If I intersect A with this guy, this is the same as the first intersect A with X, which is A. And then I take minus Z. We can imagine the situation like this. This is my big space X. And there is somewhere inside Z. And there is A. This. And then B is like this. Okay, I also need to check that this I need to check that this condition is equivalent to this condition. Well, it's also pretty easy to see. So we know that the Z the complement of Z is inside the interior of A is exactly equivalent to that X. Well, if we know that X well, the interior, we know that interior of B is X minus closure of Z. And since closure of Z is inside interior of A, this implies that the X is completely covered by int of A. X, X minus complement of Z is the same as interior. So X minus closure of Z is the same as interior. Or so what I'm saying is the interior. And the other way around, X minus interior of B is a complement of Z. And since complement of Z is an interior of A, this means that this means okay, so before proving the theorem, which I'm not sure if I can give you the full proof with all details in the remaining lecture time, but anyway. Let's see. So because we also want to consider some examples later of using this theorem, which might be more important. So okay, so let me consider U be a set of a collection of subspaces in X such that the interiors cover X. And then we can define the following abelian group. So it will depend on the choice of U, this collection of subspaces in X. So this will be a subgroup in our Cn of X. And so this is a subgroup generated by a particular, so it's generated here continuous maps like this, and this subgroup is defined by imposing some extra condition. So there should be not all possible maps, but there should exist J in this set such that sigma, the image of sigma is inside UG. So imagine that this is X. X is covered by some patches. Yes, and we only consider singular simplices which can be put completely inside one of the patches. Okay, and okay, this is the definition. So this D, so we had the D, the boundary homomorphism. Like this, and as before, so if it induces, it will induce a D on this subgroups. This is by the same argument as before. So if you consider just singular simplices in some where an image restricted line in some of these sets, so the D is not the action of D will keep them inside, right? Because D is just taking some boundaries. And this is still will be again. So this means that we have defined chain complex. X, and therefore we can consider the corresponding homology groups HN. X, by definition, the homology of this chain complex. So the kernels of this map divided by the images. So we now argue that this Hn of U is more or less the same. It's actually isomorphic to Hn of X. This means we can calculate homology by considering this simplex singular simplices inside particular patches. We can always consider them to be sufficiently small. namely, I want to show the following lemma. Inclusion. So this is inclusion of abelian groups, which we defined before. And so this is of course a chain map, because D is just given by restriction. And the statement of this inclusion is a chain homotopy equivalence. Chain homotopy equivalence means that chain homotopic to identity. We already defined what is a chain homotopy means. And so in this particular case, this means that there exists a ROR, should be a chain map in the opposite direction. Such that those compositions are chain homotopic to identity. So in particular, this will imply that this is the chain homotopic to identity. This means if we take a push forward of them, this composition of push forwards on homologies, this would be just identity. This and this, this and this order. This means that the I star should be isomorphism. So I star is a map from HMX to HX and isomorph. Essentially, we want to show as a more related statement, but essentially, I want to show that this is these groups are isomorphic. So the proof for the excision lemma. Once we prove this lemma is the proper excision theorem will be relatively simple, but the lemma, the proof of lemma is hard. I warn you. Okay, so and long. So I might because of the time constraints, and maybe because if I'm going to be too bored with technical details, I might need some technical details. And so you can look. Well, you can find the proof in Hotshot. There's all the details in Hotshot. But anyway, let me. Okay. So So one needs to prove this. One needs to introduce some auxiliary notions. So first, we can consider some general situation. Let me fix some n, integer n, which should be sufficiently high, sufficiently large. And the variable should be, whenever index should be larger than whatever index n we consider here. Okay, and so this will be a subgroup of singular chains in Rn within space. So again, so all possible generators here are the maps from delta n to n. And here we want to consider only maps which are linear. What this means is linear, so we can understand, we know that this can be understood as realized as a subspace in Rn. So the n-dimensional simplex can be realized as a subspace in Rn. The triangle delta 2 can always be realized in. Actually, I forgot, have been using the upper index or lower index?
N plus 1.
Hmm?
N plus 1.
Well, yes, but you can also consider this as in R2. I mean, the R2 inside, well, you can also realize it in R3. But if you want, that doesn't matter for us. But you can always realize it in R2 inside R3, which is given by this condition, the sum of all coordinates is 1. Subspace in R plus 1, which is given by this condition. But in any case, yeah, you just realize this is you can realize it also in n plus 1, and so this map is linear, means it's a restriction of a linear map between these Euclidean spaces. Okay, let me elaborate a bit on this. So it's completely specified, such map, completely specified by images of its vertices. So if delta n is, so if we choose, as usual, the vertices, the standard simplex to be Vn, so they are mapped to some points Wi. Inside, because of linearity, whenever since the points inside these guys, a linear combination, by definition, the linear combination of these vertices, the full map is completely specified just by defining the image of the vertices. Okay, so so I can alternatively understand this LCM as a free abelian group generated by the sequences of this form, where Wi's are elements in this Rn. So I use the same notation as for the standard simplex, but here is a sequence of points in Rn. And actually, unlike, well, I also have to, for convenience, I also want to define this -1. So this is what is called linear chains. Well, to be precise, the linear singular chains. Because again, the image of this map can be degenerate. In particular, the triangle may map to something like degenerate to an interval or to a point. So singular linear chains, and this is why this L is here. But we also want to, for convenience, we want to extend this definition to index -1. So before we for visual chains, we consider it for -1 just to be trivial, but we want to, it's natural to understand this is a free abelian group generated by an empty sequence. the single generator, so it's just default. Okay, so one more thing today is that we can similarly define the following as a D here by taking, so the generators here are the sequences of points in Rn. So let me take some sequence here. And so again, here the I understood as the points in R big M. And this is mapped to the sum of this. And well, I need to extend this definition to this to the case with one vertex. So this is mapped. This is just empty. It's not short. So it's empty. So I have material map from LC. This is the case where n equals 0. That's the definition. Not for the usual case we had it before. We got just 0, but it's not short. It's like this. And you see, I mean, we still have this property. Just proof as before. So proof was purely combinatorial. Okay, so this is just the beginning, but let me stop here.